Hi everybody. Okay, I promised you a little demo on how to set up an Excel file on the in-class exercise that we worked today. So here's that. Remember, the issue was we have some stream that we want to know how the dissolved oxygen is going to be changing as a result of some pollution that's being added to it. So we've got a river which is flowing at 3 cubic meters per second. We know its temperature, BOD content, dissolved oxygen. And then the pollution that's going into there contributes flow, temperature. It's got some initial ultimate BOD, dissolved oxygen, and so on. So this is how we're going to set it up in Excel for the known deoxygenation and reaeration constants that are provided here, the known river cross-sectional area. What we're going to use is the Streeter-Phelps method to calculate the deficit in oxygen as a function of time. And once we know the deficit, then we can determine the dissolved oxygen. So let me show you what I've come up with so far in Excel, just kind of as a starting template file. So here's just a summary of the problem. And the first thing I'll do is just copy over the K values that we know. So 0.53 for the reoxygenation is 0.75. The deoxygenation is 0.53. Okay, so the flow rate of the river was 3 cubic meters per second. The flow rate of the pollution was 32.4 cubic meters per minute, but then divide that by 60 to get cubic meters per second. So the mixture is just simply the sum of the two. The temperature was 5 and 35. And so the mixture is going to be, it's this flow rate times this temperature plus this flow rate times this temperature. That's cell C7. I can't click on it because it's centered in the way. Okay, and I need to put these parentheses around here, and it's divided by the flow rate. So the mixture temperature is 9.6, and you'll remember that in class we just used 10 so that we didn't have to interpolate the dissolved oxygen, although we could have done that. The dissolved oxygen of the river was 7. The dissolved oxygen of the pollution was 1.1. And so therefore the dissolved oxygen of the mixture, we're going to use the same mass balance approach that we did here. In fact, I could drag that formula down. If I'm going to drag it down, I'd want to anchor the references here to the flow rate and these. So with that anchored, I can drag it down, and now it is weighting the dissolved oxygen on the basis of the fixed flow rates. So, that's just kind of an Excel trick, so I didn't have to type that formula in again. So the mixture dissolved oxygen concentration, 6.1 milligrams per liter. Then the ultimate BOD for the river was 1. For the pollution was 50. So again, I can drag this down and get the ultimate BOD of the mixture. So let's just take a moment to double check that these values are consistent with what I showed you in class today. So it was saying the mixture temperature concentration, the temperature was 9.6 Celsius, the dissolved oxygen 6.1, and the ultimate BOD 8.47. So yes, I think we are on track. All right, so the initial deficit is saying, here's what the dissolved oxygen concentration is. What should it be? So at this temperature of 10 degrees Celsius, the saturation dissolved oxygen should be 11.27. So if that's how much maximum oxygen there can be at the temperature of 10 Celsius, then our initial deficit, if the dissolved oxygen is 6.1, then the initial deficit would be, let's set that up as a calculation. So it's the saturation minus the actual concentration of dissolved oxygen, 5.17. And again, that's what we had for the initial deficit in the hand calculations today. So we're just kind of setting things up with what we already know to be true from our hand calculations, because in the homework assignment, it will be beneficial to be able to play around with things and have it automatically calculate. So here's the Streeter-Phelps equation. We want to, as a function of time, and using all of these constants, find out how the deficit changes as a function of time. And how much time? Well, I don't necessarily know at first until I take a look at what the sag is. And so I may want to go in and change it to like increments of 0.1 or 0.2. But just as a starting point, let's see what it looks like if I have it in half-day increments. Okay, so now I'm going to start typing this equation in into Excel. So it is K sub D, and I'm going to anchor the reference by pushing the F4 button, times the LA, and that is the mixture of the ultimate BOD of the mixture. So that's this one. Anchor the reference, divided by KR minus KD. And I need to anchor those references because I'm going to be dragging this formula down. So I want it to always look in those cells. Okay, so I've done this first part of the equation. Now it's times, in parentheses here, EXP. That's what we do for e to the power of. Okay, minus K sub D times whatever time we are on. So the time for this row is going to be A15. So I'll type in A15. And I need to anchor that reference to the K sub D. So I'm going to press F4 to make sure it's got the dollar signs in there. Okay, so I've got this term entered in. Now minus, oh wait, I need to close the parentheses to get the exponential function finished. So minus EXP of minus K sub R, so that's here, anchor the reference by pressing F4, times the time, which is cell A15. I have to type that in because, well, maybe I don't have to, but I've typed in the cell reference where the time value is. Okay, close parentheses, and then close parentheses again for this one. And you can see that it just, like in black and bold, it kind of gives you that visual indicator that we've closed parentheses around the exponential function. So now I need to do the plus D naught. So that's the initial deficit. So plus this initial deficit, anchor the reference, times EXP of minus reference KR. So that, anchor it, times time, which remember is cell A15. Okay, so that was a journey. I've got it typed in, enter. Initially, the deficit is 5.17, and that's what we already knew to be true. So far, so good, right? As I drag this down, the deficit should grow. So if I drag it down through maybe 4 days, the deficit is not growing. And it's because my time is too big. If we go back to the hand calculations from earlier, remember that what we saw is that the critical point was 0.25 days. And so we've just blown past it. The deficit is already recovering. And so this is where I was talking earlier about how I don't know off the bat what kind of time scale to use until I start to do the calculations. And so maybe I'll do 0.05 and 0.1. And let me have it show by increasing the number of digits that are visible. All right. Okay, so the deficit grows and then it begins to recover. Maybe I even want to do it in smaller increments. So maybe I'll do 0.02, 0.02, 0.04. So let me drag that down through maybe like like 0.78 days. All right, so this, let me double click. Oh, the deficit, that's the formula that I typed in, here. And let's just check when I extend it down, like once you've got the formula typed in once, you don't have to type it a bunch of other times. We can either click on this extra thick green part and drag it down manually, and it'll apply the formula, or you can double click and it will extend it for as long as there's things to the left. Okay, so what it's showing is that the deficit gets bigger, but then it starts to get smaller. And what we found from these hand calculations earlier is that the maximum deficit would be at 0.25 days. And so that does look consistent with these calculations, where the deficit is the biggest at 0.24, 0.26. So it's happening at 0.25 days. And so if I wanted, I could continue this further, or maybe once I get to a certain point, I could go in bigger increments. And so from 0.7 to 0.8, 0.9, 1, 1.5. Like, we're just kind of curious to 3, 4, 5, 6. The deficit's getting smaller and smaller, 7, 8. It eventually should reoxygenate the river all of the way. So if this is modeling the deficit, remember that according to what we saw in class, the deficit is what we're calculating. Dissolved oxygen concentration is saturation minus the deficit. So dissolved oxygen is saturation, anchor the reference there, minus the deficit. Okay. So now I could do a graph of how the dissolved oxygen concentration is varying over time. So you can see here I had a graph from before. Let me just delete that and start from scratch. I'm going to do a figure, and I want it to be an XY that does not show the individual data points, and we'll smooth the lines. Okay, so now I need to select the data. So this is going to have, on the horizontal axis, it'll be time in days. And then on the vertical axis, we want to have the dissolved oxygen concentration. Okay. Something tells me I've got an issue here. Let me start over. So on the, maybe I put it on the series name. The X values are going to be time, and the Y values are the dissolved oxygen. Okay, that's more like it. Okay. So there was a deficit to begin with, and let me put in some just axis titles would be good. Here we'll have time in days. And then on the vertical axis, this is DO concentration in milligrams per liter. And there's no sense in showing all those extra digits of precision there. Let me right click, format axis. I'll have it show only 0 decimal places. Now it's just the number. Here I don't need to show decimal places there either, so 0. Maybe I will though if I zoom in, because it would be interesting, 1 decimal place. It would be interesting to zoom in and just see it's sagging to the low point. So let me over here zoom from 0 to 1 day. And here let's have it show from maybe 5 to 8. And that allows us to see the curve a little bit more. So here's the sag, the lowest point of the sag. In fact, maybe I want to see those decimals after all. Let me zoom in even more. So like from 5.5 to 7. It's just a way for me to see the curve in a little bit more resolution. So anyways, this is how we've set up the calculations in Excel. And what's nice is in the homework, you're going to be asked to do some calculations related to like the maximum amount of, let me show you on the homework, like using a spreadsheet you developed, identify the maximum wastewater flow rate that could be discharged and still keep the river dissolved oxygen concentration above 4 milligrams per liter at all points. Okay, so what if in this example that we're working on, let me just zoom out here, format, so that it includes from maybe like 3 to 7. All right, so how high could the wastewater flow rate, so here's the wastewater flow rate, I can change that, and I don't want any of these dissolved oxygens to go lower than 4. So this is kind of like a goal seek activity here. So if I gave it 1 cubic meter per second of pollution, you see now there's a lot worse dissolved oxygen because there's more BOD in the mixture. So what about 1.1? Okay, let me do this, equals min, and then that's going to return the minimum value of this whole range. Okay, so it's easier to see. If my goal is I want the minimum to be close to 4, how high could I take? 1.2, 1.25. We're getting closer. 1.26. Of course, if you remember 111, we had this data what if analysis goal seek where we say we want this to be 4 by changing the flow rate of the pollution. Goal seek, and it says we could get 1.27 cubic meters per second of pollution, and then the worst sag would be 4 milligrams per liter. And interestingly, the sag location, like the worst sag, it was in a different spot now. So when we had that initial flow rate of pollution, remember the low point was at 0.25 days. Now the low point is at a different location. So it takes longer for it to reach that, that low point. Let me change my zoom out here to maybe 5 days. Okay, so we can see the sag and the return to the dissolved oxygen dissolved oxygen concentration a little bit better. So this is a good representation that we had some initial deficit. It's getting closer to saturation. Saturation's 11.27. So hopefully that illustration is helpful and will allow you to solve this problem 8 on the homework assignment that's due next week. If you've got any questions, feel free to stop by my office. I'm always happy to talk to you or help you to troubleshoot the spreadsheet if you have any issues as you put it together.